All right, get ready for this one. We're going to talk about a piece of plain old stainless steel that was given two, seemingly totally unrelated superpowers. One of them is the ability to bend sound, which is cool enough. But the other, and this is the really wild part, is that it basically learned to hate water.
So just picture this for a second. A lotus leaf, right? It's nature's perfect example of water repellency. Water just beads up and rolls right off it. Now, what if you could make a tough, solid piece of industrial metal do the exact same thing? Well, that's exactly what researchers at IIT Kanpur managed to do. And here's the kicker, it was almost by accident.
The secret here is a property called hydrophobicity, which, is just a fancy way of saying how much a surface hates water. Scientists measure this with something called a contact angle. The bigger that angle, the more a drop of water balls up and refuses to stick around. So think of it like this. A flat puddle is 0 degrees, but a perfect little sphere just sitting on top is 180. And this is the number they hit, 145 degrees, on steel. That is a gigantic leap in water repellency. It actually puts the metal in a special category called quasi-superhydrophobic. So it's not just repelling water, it's practically shoving it away.
I mean, just look at the difference here. A normal, smooth piece of stainless steel, it sits at around 98 degrees. Water still kind of clings to it. But after these researchers did their thing, that angle shot all the way up to 145 degrees. That is literally the difference between a surface that gets damp and one that stays almost perfectly dry.
So, you're probably thinking, wow, creating self-cleaning, anti-rust steel must have been the whole point, right? Nope. Turns out, making the steel hate water was actually just a happy accident, a side effect of a completely different and, you could argue, way more complicated scientific mission.
They weren't trying to make a better raincoat for metal. No. What they were really trying to build was a maze. A maze designed specifically for sound waves.
And this gets us to the real heart of the research, something called a phonic crystal. Okay, so a phonon is basically a tiny particle of sound or vibration. So a phonic crystal is a material that's been engineered with this repeating pattern on a microscopic level, all designed to mess with those sound waves. It can stop certain frequencies dead in their tracks, guide them down specific paths. You get it. It's a sound maze, baked right into the metal itself.
So, if these are so cool, why don't we have them everywhere? Well, because trying to build one of these phononic crystals out of a strong metal, like steel, is just incredibly hard. The old-school methods you'd use in a clean room, they are painfully slow and cost a fortune. Other techniques often end up creating these tiny, delicate structures that would just crumble under any real stress. And yeah, we have 3D printing, but that's mostly for plastics. It's not really ready to make these kinds of super strong, super precise metal structures on the cheap.
And this really sums up the problem they were trying to solve. You've got the old way over here, slow, super expensive, and the results are often way too fragile. And then you have the goal, a process that's fast, can be scaled up, doesn't break the bank, and most importantly, create something that's tough enough to actually use. That was the holy grail. And the solution they came up with was just brilliant. It was so elegant. Instead of trying to build something up, they just dissolved material away, using this really clever process. It's called wire electrochemical micromachining, wire ECMM for short. So forget about force and grinding. This whole process uses a tiny wire, thinner than a couple of human hairs, as its tool. And the wire never even touches the steel. Instead, an electric current flows through a special saltwater solution, and it just precisely dissolves the metal away, almost atom by atom. There's no heat, no pressure, no vibrations. It's just clean, precise, microscopic sculpting. The process itself is almost ridiculously simple. First, this little electrified wire just glides over the steel, dissolving a set of perfect parallel grooves. Then, they just rotate the block of steel exactly 90 degrees. The wire makes a second pass, dissolving another set of grooves that crisscross the first. And what's left behind? A perfect microscopic grid of tiny steel pillars, the exact phonic crystal they wanted to make in the first place.
And this, right here, is where our story comes full circle. Because the wire ECM process, it didn't just work, it worked spectacularly well. It completely solved the manufacturing headache, but in the process, it unlocked that second, totally hidden superpower in the steel.
See? It turns out that the very same grid of microscopic pillars that was designed to be a sound maze also just happened to be the perfect texture for making water bead up and roll away. The one process gave the steel this incredible double identity. It nailed its main goal, creating the phonic crystal, and at the same time, it created that amazing water-hating surface we talked about at the beginning.
So, success number 1 was a bullseye. The super precise spacing of those tiny pillars creates what scientists call a band gap. You can just think of them as no-go zones for sound. So when a sound wave with a frequency that falls inside that band gap hits the material, it just can't get through. It's stopped cold. The material becomes a perfect sound blocker for those specific frequencies.
And you know what the best part is? Unlike structures made with other methods, these things are tough. The researchers ran the numbers, and their analysis confirmed that these little pillars are incredibly strong. They won't buckle or bend under normal conditions. You'd basically have to push them to their absolute breaking point to make them fail. In simple terms, they're mechanically robust. They're ready for the real world.
Okay, so let's step back. We have a fast, cheap way to make a tough material that can manipulate sound and repel water. What does that actually mean for us? Why should we care? Well, the potential applications are just huge. For communications, this could lead to way better filters inside our phones. Because it repels water, it's perfect for making tiny lab-on-a-chip medical sensors, or for creating self-cleaning surfaces that never rust. And of course, you can build tougher, more precise ultrasonic tools, or even create waveguides that can steer sound energy exactly where you want it to go.
And that really gets us to the big takeaway here. This isn't just about one cool material. It's about a whole new way of making things. It opens the door to creating an entire new class of smart materials with properties we've only dreamed of. So the real question is, now that we have this amazing new tool in our toolbox, what's next? What other incredible dual-power materials are just waiting for us to discover? What are we going to build?